Hi, my name is Dana Golden. Let's get back into it. Tree-based algorithms and unsupervised learning. So, review of classification. You have logistic regression, you have decision trees, you have random forests, you have support vector machines, you have k-nearest neighbor, you have naive Bayes. You're trying to separate multiple classes of objects. You know the classes. This is a supervised form of learning, and tree-based models are another version of that. So classification regression trees. Decision trees split the data into smaller groups based on the values of input features. Classification tree predicts a category by asking a sequence of yes or no questions. Is income greater than 50,000? Is age less than 40? The final prediction is the most common class majority vote in the group. A regression tree predicts a number by averaging outcomes in each group. Trees are easy to understand and can model complex decision rules. Decision trees work best when the relationship is non-linear. There are clear thresholds or jumps, tax brackets, eligibility rules. Linear models are better when the effects of inputs is smooth and additive. The goal is interpretation, not prediction. In practice, trees are useful for particularly decision trees outperform when there are jumps. They can handle both numbers and categories and automatically capture interactions. Like if age is greater than 50 and owns a house. They're also the basic building blocks of advanced models like random forest. So Gini index measures the probability that random observation will be misclassified. Lower Gini is a more pure group, mostly one class. The formula for binomial classification, Gini equals 1 minus p1 squared minus p2 squared. Entropy measures the uncertainty or randomness in a group. Entropy is lowest when all class observations belong to one class, is highest when the classes are evenly mixed. So the entropy is a measure of randomness. For introduction in decision trees and regression trees, we choose splits that most reduce the variance of the outcome variable. The goal is to create groups where the values are as close as possible to their group mean. Pruning helps reduce overfitting by simplifying the tree. There are two main types. Pre-pruning, so early stopping during tree growth. Set the maximum depth for the tree. You require a minimum number of samples to split or be in a leaf. And you limit the prior number of features considered to be split. Post-pruning, trimming after the full tree is built. I have cost-effective pruning. Remove branches that don't involve a trade-off between that don't improve a trade-off between accuracy and complexity. Reduced error pruning. Keep only the branches that improve performance on validation data. Enforce a minimum leaf size to avoid splits on small groups. Here's a classification tree visualization. It's the outlook. We're trying to decide if it's going to rain or not. We're going to try to decide whether or not we should bring an umbrella. Sunny, humidity is less than or equal to 75. There are a lot of yeses. Greater than 75, there are 2 no's and 1 yes. So we classify this one as no. If it's overclassed, yes. If it's rainy, is it also going to be windy? If yes, no, we do not need an umbrella. If no, then yes. I'm not exactly sure what this is predicting. It's not whether or not you need an umbrella, but it's the outlook, and it's predicting whether or not the outlook is yes or no based on features. Bootstrapping means sampling from the original data set with replacement. Each new sample may repeat some data points, helps estimate uncertainty, such as standard errors without strong assumptions, widely used in statistics and econometrics. Random forest builds many decision trees using bootstrap samples of data, a random subset of features for each tree. For classification, each tree votes and the majority wins. For regression, it averages the prediction from all trees. Idea: combine many simple models to improve accuracy and improve overfitting. So that's kind of the idea of random forest, is we're combining a bunch of individual decision trees that each learn a little bit about the space to reduce overfitting. So we have an instance, and it goes through a bunch of different trees. They're trained on different portions of the initial sample. We have a majority vote, and then we have a final class. When to use random forest usually have lower bias but higher variance to a single decision tree. They are less likely to overfit on small data sets compared to one tree. They're harder to interpret since predictions come from many trees. And building them takes more time, and they can be sensitive to random samples. Thank you, and I'll see you next time.